There we go. And could I just get a quick confirmation, Manuel, that you can see the screen presentation?
Yes, we can see the screen. Thank you.
Perfect. Thank you. So good afternoon, everyone. Thank you for giving me the opportunity to share some statistical discussions with you. For those of you, and I'm looking at some of the names coming in, and I recognize a few, and many of you I don't know. But for those that don't know me, my name is Anthony Carra, and I was actually local and part of the Northeastern chapter of the ASQ there for some time. And as Manuel mentioned, I've spoken once or twice. I've moved around since then. I'm currently calling in from Bay Area, California. But definitely thankful for the opportunity to speak. So Manuel and Mark, thank you for giving me the opportunity, and I look forward to sharing some things that I picked up over the years, and we'll leave some time afterwards for Q&A discussion as well. Before we get started in the content here, my journey in statistics probably goes back to as early as a misspent youth in the pool hall in my teenage years, where I kind of learned some of the basics about probability and statistics, and then years later I would learn a more practical application in the med device industry through both process validation applications, process improvement applications, and things of that nature. So those will be that'll be the context of what I'll be sharing today and be opening up for conversation. Very often, I do get called in for statistical discussions, whether it's when I'm actually as a consultant and I'm called in to do that type of work, or if I'm holding a role within an organization. It's usually not too long before folks figure out that I know a thing or two about statistics, and usually folks will come to me when the statistical study doesn't go well, right? So when you're trying to pass a validation and the data it's just not working out well, or gauge R&R that's not giving you the result that you want. So that's usually when I get called in. And the lesson that I want to share is more so, setting up a statistical study properly from the beginning, right? There's a lot of times when I get the data set after the fact, it may not have been set up correctly in the first place. So just sharing some of those lessons and the considerations for both the planning as well as the analysis of statistical studies. So some basic principles we'll go through and some fundamentals. We're not going to dive into the math, at least in the primary content. If you have some applications you want to talk through when I get through, I'll be more than happy to jump through that. So, just as a matter of kind of logistics, Mark had mentioned to me that should you have any questions throughout, I know everybody's on mute, but you can submit them via the chat, and then Mark or Manuel will be able to help navigate through that when we're done with the presentation portion. So brief introduction as we went through, and then what is statistics, and just kind of a high level and why we use them. I'm going to introduce a three-step process. It's very high level, and for those of you that use statistical methods, it's not going to come as a big surprise, but that's the point, right? It's basically focusing on the basics and having the discipline to kind of stick through that time and time again. And then we'll talk about some of the considerations for the planning and analysis. And as promised, we'll open up some time for Q&A. So first and foremost, what is statistics? So in the basic sense, excuse me. In the basic sense, it's the methods that we use to collect, process, and interpret data. And there's two primary avenues that we look at. There's the descriptive statistics, which is basically the summarization and characterization, so we can describe the data that we have and whatever physical phenomena that data is intending to represent. And then secondly, we have inferential statistics. This is where we want to use data, we want to come up with a conclusion or some estimate that we can claim about a population. Right? The very essence is we're not going to be able to measure everything, so we use a sampling and calculate what we call a statistic to represent represent the population, to either describe it or to draw some inference from it. At the end of the day, statistics is a very practical math that we can use for making data-based decisions for real-world problems. So the statistical method, it follows a process like anything else, right? So in statistics, basically, summarizing in this tutorial, we want to collect, organize, analyze, and interpret some information. And with that, we have data going into that process and then drawing out either the inference or the decision. So this process shows it's very linear, right? You can't necessarily jump in. As I mentioned, a lot of times folks will come in on the analyze part where there's some issue with the data or drawing some interpretation. And what you're going to find is we're going to want to have that discussion prior to collecting the data and doing the analysis. As Ben Franklin is famously quoted for, if you fail to plan, you're planning to fail. See planning as a virtue, and again, anytime you want to embark upon some statistical study of some part or some manner, the time you spend in planning is going to pay off in dividends. And there's another famous quote from Stephen Covey: begin with the end in mind. Right? One of the 7 habits of highly effective people. And this is that 3-step process that I mentioned. Beginning with the end in mind, if we take that diagram, first answer the question, what is the decision or claim that you want to make? A lot of times folks will come with me with the data and they don't even know what a conclusion. They just know that med device application. They just know that they have a filing that they have. They want to be able to make some claim, and they have some data, but they don't necessarily see how to connect the dots. So this is where knowing the claim that you want to make first and foremost is going to be key. Then from there, it opens up the statistical tools or methods that you can use to support that decision or claim. Not every method can be used for every application. And just because you used a method one time doesn't necessarily mean it's going to be the right tool for the next application. So starting off with the decision or claim that you want to make, back into what tools and methods are available to you to support that claim. And then once you know that, it is what are the data that you either have available or you're going to need to acquire or obtain to input into those methods so that you can make that claim. So again, it's not, it may be nothing new that if you've been working with data and working with statistics, maybe nothing new, but the idea of beginning with the end in mind. Clearly state the question that you want answered, and then we can come up with statistical methods and analyses that can support that claim. So what are some of those applications, right? If you want to think to yourself, all right, what kind of conclusion can I draw? What kind of decision can I make? These are just some of the common applications. There are many, many more. But from a descriptive analytics perspective, you may want to see where the central tendency may be, such as the average performance of a particular piece of equipment. You may want to understand the spread or variation that a process may be demonstrating. Or you may want to understand the shape or the distribution. All of this can be answered with simple descriptive analytics tools and methods. There may be times when you want to identify a relationship between 2 variables. We'll see that in correlation studies where maybe we have some historical data and we want to see if there's a potential relationship between 2 items. Or in a proactive manner, in design of experiments, we may want to take that relationship a little bit further and actually demonstrate cause and effect relationships. The big difference between those two is with the historical data, it's more of an observation, and you may be able to demonstrate correlation, but correlation doesn't always mean causation. Right? Just because you see a relationship doesn't always mean that that one of those variables causes the other. However, in design experiments where we're actually running a structured experiment, you can make more of a claim of cause and effect. You may want to evaluate the performance of a process or a piece of equipment. And when I say process, it's not just manufacturing process. It could be a business process of some sorts. The cycle time of processing a sample through a laboratory, as an example. These are all things where you can use data to evaluate performance, and you could use it to establish a baseline of your current performance level. And you can also use it predictively to determine what future performance levels may be. For those of you that do validation work, if you're using statistical tolerancing, that's exactly what we're doing. We're basically making a claim that with a certain degree of confidence, that a certain percentage of future measurements will fall within a particular range. So we can use that for evaluating both current and future performance levels. And then as well as trending, and the same idea for trending, we could look at historical trends and we could see if something is trending up or trending down or maintaining even status. And here's where it gets a little tricky. We can forecast. It's very often said that you don't want to extrapolate beyond the data that you have. But when you have time-based data, you can come up with a forecasting model to predict future trends within some range. And then the last one that we have here is monitoring and control. So if I take evaluate performance snapshot in time, or if I'm looking at a trend over time, that's fine. But the monitoring and controlling is something that's a little bit more active. This is where you've heard terms like SPC tools would come into play, where we can actively monitor how something is performing, and maybe if it intervenes, step in and control only when needed. This is key, especially in SPC. You may be tempted to make adjustments prematurely. Proper statistical techniques will basically guide you towards appropriate level of control. And as I mentioned, these are just some of the most common applications, and there's much more. Similarly, for every method that we have, there's an assortment of tools. And as I alluded to before, not every tool will work in every application, but being able to understand which tools are available to you based on what you want to do. If you just want to graphically display the data, we call it data visualization. If you want to show folks what the data are saying, we can use graphical methods such as, and not limited to, histograms, box plots, and run charts. And each one of those tools will tell you different things. A histogram will show you central tendency, spread, and overall shape. Box plots, maybe more so just central tendency and spread. Where run charts will show you variation over time and any potential trends and such. Your descriptive statistics then is a calculation, if you will, that can summarize the data that you have in some of these charts. You can, some degrees of central tendency, such as mean or median, of where the data tends to be centralized. You can have your variance or standard deviation to demonstrate the spread. You could also see skewness, which again is talks a little bit to the shape of your distribution of your data. From there, we can actually start making some inferences, start making some decisions. First and foremost, there's comparative methods. The t-test is the average of one population statistically different from another. The Mann-Whitney test, which is looking at that from a perspective with attribute data. ANOVA analysis, where you have maybe more than two groups that you want to determine if there's a difference among. Same thing with chi-squared. Your relational methods, as I alluded to before, you may want to see if there's a potential relationship between or among two or more variables. You have the basic linear regression, where you have two variables and you just want to see if there's a linear line. That can then progress into nonlinear. Maybe there's curvature and such, but it's still that relationship between two measures. your logistic regression. Maybe you have an independent variable or an X variable that could vary, but your outcome, your output measure, your response is attribute, right? High or low, pass or fail. In which case, logistic regression models will help. And then you have just general linear model, which is a pretty robust approach to exploring for potential relationships among variables. And then performance measures. And different companies choose different measures and how they want to measure it, but the intent is to demonstrate performance, both current performance and potential future performance. We can do things like capability analysis. I mentioned before statistical tolerance intervals. And then when you're talking about performance of your measurement system, you can have a gauge R&R to demonstrate the repeatability and reproducibility of your measurement system. And again, these are probably some of the most common ones that you may come across. And there's more, right? If you'll find that sometimes you'll have a weird application. You want to be able to answer some question, and you need to kind of dive into the stats book and see what other tools are available to help support our claim. So if we kind of walk that backwards, right? So the first step was, what are some of the conclusions we could draw? We talked about some of those. The last slide was, what are some of the tools and methods that are available? That was step 2 of the 3-step process that I mentioned. And then the third step is the data that you need to put into the method, into the analytics. And there's 4 main types of data that you want to consider. And again, it's sometimes you're just limited by the data that you have. Other times is, especially when you're in development, you have an opportunity to determine what your measurement method is going to be, and understanding the pros and cons of the different data types is going to be beneficial for selecting the best measurement method, or one of the ideal measurement method for what it is that you want to measure and characterize. But the data types that we have, and it goes from the top down, I would say it probably goes from the least expensive to acquire, but with that being maybe I don't want to say the least valuable, but you need a lot more information. You need a lot more samples to be able to draw any conclusions from that data. Whereas as you go down the list, it tends to get a little bit more expensive to acquire that data, but you gain so much more knowledge, right? And that's where you have to understand the trade-off. So the first one is nominal. It's purely a categorical attribute, and there's no specific order or value. So for example, you can look at an object and determine the color, red, yellow, or blue. And then obviously you can use that for sorting purposes and things of that nature. But there's no clear designation between, there's no ranking between red, yellow, blue. They're just, you can put them in any order and it really doesn't matter. The next level where you gain a little bit more information is ordinal. And there too, it's a categorical attribute. But the main difference here is that there is an order. There is a ranking of sequence, but not necessarily a relative ranking. So for example, small, medium, and large, you can put those in order, and there's a natural order that they follow, small, medium, and large in size, and size increases, but there's no relationship. We really can't say that medium is twice as big as small, and or large is 3 times. You really can't say that. Same thing with agree, neutral, and disagree. There's a relative ranking. I'm sorry, there's a natural ranking, but there's no relative value among those. And similarly, Likert scale would maybe be another one that you may come across, where rank a number between 1 and 5. And with those, 2 is not twice as better than 1. It's just a ranking system. Next would be interval. Now, interval is when you actually start getting numerical data that you can do some calculations with, and they actually have meaning. It's sequential. Now, it may be sequential, and there could be a relative ranking between the 2, but the ratios don't necessarily have any practical meaning. So, for example, temperature is a perfect example. Degrees, right? And So 10 degrees centigrade to 20 degrees centigrade. You can get an idea of what that measure is, right? And what the relative risk is, right? You really can't say, though, that 20 degrees is twice the temperature of 10 degrees. That doesn't have any practical significance. It doesn't make sense, and that's just not how the temperature scale works. But there is that natural order, and there is kind of that fixed relative ranking between categories. And then last but not least is your ratio data. This is numerical, it's sequential, and the ratios do have meaning. So this is where take a linear measure, whether it be with a ruler or a caliper or scale. The ratios make sense, right? So if you have something that measures 2.4 millimeters, 2.54 millimeters, and you have something else that measures 5.8 millimeters, we can say that 5.08 is the same as 2 times that. We could say that measurement B is twice that of measurement A. And I mentioned, right, and the reason why, some of them are, why I say that, from the top, it's less expensive. Usually it's something visual and doesn't require any special equipment or training. And just by glancing at the thing, you can quickly make the assessment. So it doesn't necessarily take a lot of time or special equipment, which would go into the cost. Conversely, go to the other side with ratio, you need some special equipment. Sometimes you even need training and the time that it takes, to actually take the measurement, record the measurement, and things of that nature. So, and again, understanding the different data types, the claim that you want to make, and what you're going to need is going to be key when selecting the your data acquisition method, if you have that opportunity. If not, correctly understanding what category the data that you have falls within, because that will then determine, from a choice of tools, statistical tools that you'll have, which ones you'll ultimately have to use based on the data that you have. So step one, we want to talk about planning the study. So now we want to, when you're considering the planning, the forethought of what it is that you want to do, as I mentioned before, begin with the end in mind. What is the decision or claim that you want to make? Are you trying to make a claim about performance as you would in validation? Do you want to make a claim about variation in your process as you would as you're doing process characterization? Understanding the goal or the objective of what it is that you want to do is going to be key. The statistical tools and methods that you're going to need, and then the data that you have, right? So step one of your plan is going to be considering those 3 elements that I mentioned before. And then you're going to want to draft a protocol. You want to stake a claim and draft it down. And depending upon the industry that you're in, sometimes that's a very formal protocol. But even if it's not required in your industry, highly encourage, write down the plan, because you want to make sure that the plan gets executed. If a team starts going off and collecting data ad hoc and things of that nature, you may not get to the end that you're trying to get to. So you want to set up a protocol that will help guide the team towards executing your statistical study as intended to reach the objective. So with that in your protocol, you want to define your goals and objectives of the study. You want to define the sampling plan. And in the sampling plan, it's just not the number of samples. How are you going to acquire those samples? How are you going to make sure that bias does not come into your study? How many samples do you need? The stratification of the samples, those all come into play by first understanding the thing that you want to measure. So you come up with your sampling plan, you spell that out, and then the analysis methods. You're giving somebody instruction, hey, you're going to go collect this data, and this is how you're going to analyze it. You want to be able to state that up front, because again, it's going to lead toward making the claim that you want. You don't want to necessarily leave it open-ended, because a tool may be selected, data may be gathered, a tool may be selected and not necessarily answer the question that you're trying to have answered. So define the methods that are going to be used and define the acceptance criteria if applicable. Not all statistical studies will have an acceptance criteria. Validation is an example of one that does. But if you're doing a DOE where it's a screening DOE or a characterization DOE, or even an optimization, just DOE in general, as you're doing an experiment, it's meant to be more exploratory to either understand key factors in your process, the variation that's there, getting that characterization, that cause and effect relationship, and as I mentioned, optimizing it, right? Finding the best possible outcome. In none of those examples is there really an acceptance criteria. You're basically just learning and refining the process. So not all statistical studies will have acceptance criteria, but if you are running one where there is a definitive acceptance criteria, state it because, again, very often what happens is teams will be tempted to stretch it and make it fit, right? If you didn't quite clearly state the acceptance criteria, say if you had attribute data and you want a C=0 sampling plan, team might kind of stretch it and say, well, it's only one and we can accept this one. If that doesn't answer the question that you want or sets you up to make the claim that you want, for example, a certain confidence and reliability claim, then the study wasn't really successful. So you want to clearly state that acceptance criteria for the team. Step 2, all right, you set the plan, now work the plan, execute your plan. And here's when you hand that off, or if you run it yourself, follow the protocol, all right? I understand that sometimes things come up and you may have to deviate. That should be the exception and not the rule. And even then, it should go documented and clearly understood, once again, because beginning with the end in mind, we want to make sure that the ultimate objective of the study was met. So it's best to follow the protocol, collect the data per the sampling plan. You want to make sure that you have the right data going into the analysis. Then from there, as I mentioned in that diagram, you want to organize the data as required for the analysis. There are times when we have some data collection sheets that don't necessarily, it's good to help simplify gathering the data, but it's not really good for analyzing the data. So we may need to organize the data in columns, say, if you're going to do your analysis in Minitab, or if you're going to do in Excel through pivot tables, right? You understand how you're going to analyze the data, organize the data in a way that makes sense. Then do the analysis. Analyze the data per the defined analysis methods. And that includes, and we're going to talk about this later as well, not just running through the calculation of the primary method, but some of verification of some of the assumptions that are made. For example, when you do a capability study or even a statistical tolerance interval calculation for that matter, there are some assumptions that need to be made. Is the underlying distribution stable? Is the underlying distribution, does it fit a normal distribution? Those are things that need to be verified before you can say that your analysis and the conclusions that you're making are valid. So analyze the data per the analysis method, including the assumptions, verifications to ensure the validity of the model or the analysis. And then last but not least, when you're executing the plan, interpret the results, right? The execution goes from the collecting of the data through the analysis and making the interpretation. Were the goals and objectives of the study met? Were in the DOE, right, as an example, did you understand, did you get to the conclusion of key X's, key factors? Did you get to the characterization equation? Did you find an optimal settings? And if there were acceptance criteria, were they met? So that all goes into the execution. And then the third step is to report the results. And here too, again, the industry you work in may or may not require a formal report. I highly encourage it in all cases. It creates a record, and it goes back. It's for traceability and just to make sure that whatever conclusions that were drawn, we can verify afterwards, or we can go back and maybe replicate if we need to, if there's any questions as far as performance. In the report, we should include all the raw data, right? Raw data for the traceability and verification of both the validity of the underlying data itself, as well as being able to recalculate the statistics and the analyses with the original data, being able to repeat those calculations. Include all the analysis files as well as the outcomes. Very often I work with clients where I'll provide the Minitab files, but they're not going to sort through all that, right? So they'll have that for historical reference, but I may out of that create a summary table of the outcomes that they can use in their reports. Summarize the data analyses, and then state the interpretation. Explicitly state the interpretation of the results, right? You don't want to just run through, do the calculation, say, here are the results, and leave the interpretation up to the reader. Again, if we had a protocol, we had goals and objectives, clearly state the interpretation of the results. We want to draw explicit conclusions regarding the goals and objectives of the study. We want to state an explicit conclusion regarding any acceptance criteria that may have been sought out, and the next steps and recommendations, if any. And here's where I say every study should result in a call to action. Maybe that call to action is to release a process for manufacturing, or it could be to release a design for distribution, or it could be to characterize a process to be implemented. Either way, we're doing this because at the end of the day, we want to gain some knowledge, we want to gain some insights so that we can drive a business result. So what are some of the considerations that should go into the planning? I've talked about them a little bit, but I'll go through them here. And from what I understand, the slide deck will be distributed, so you can go back to this as reference as well. And again, I can't emphasize enough, what is the question to be answered? I can't tell you how many times teams are collecting data, they're talking about the analysis, they're already talking about writing the report. And I have to kind of bring the team back to, well, what is the question we want answered? What is it that we're trying to answer? Let's make sure that we can clearly answer that. I can create all kinds of charts, we can create all kinds of analyses, and basically wallpaper a room. But if it doesn't answer the fundamental question, the goals and objectives of the study that we're trying to achieve, it's all for a loss. What are the methods that we're going to be using? As I mentioned before, right? Understanding what question I want answered, which methods are going to help get me there, and then the data that I have available, right? And it's not just the type of data, as I alluded to before. There's some other considerations about that data that you're going to want to think about. What are some sources of variation that might be in the data? Do I need to adjust my sampling plan accordingly? And again, that could go either way. I may want to do a study where I want to include all sources of variation, so I understand the overall performance that a customer may see, or I may want to limit the sources of variation because I really want to drill down and understand the characterization of a particular process. Knowing those potential sources of variation is going to be key in putting your plan together. The quality of your data. How good is that data? I mentioned before that there's a natural hierarchy of data, but even some of the most expensive data, the ratio data, if you don't have a good measurement method that has been validated, demonstrated through a good gauge R&R that the variation to the measurement system is low as compared to the process, the quality of the data, and hence the conclusion you draw, garbage in, garbage out, right, isn't necessarily that good. So making sure that you at least understand the quality of the data, so you know, right, how high you could hang your hat on the claim that you're making, and how many samples are going to be required. You'll want to think about that as well. And then I also hinted at a little bit before about bias, right? You don't have to just worry about the sources of variation that may come naturally, inherently in your data, but some of those ones that are controlled because of bias, whether it's sampling bias or just intended or unintended, right? Naturally, there are natural forms of bias that can be introduced when you're collecting information, understanding what those sources of bias may be, and then coming up with a sampling strategy to help minimize that bias. Or, as I mentioned, in some cases, take advantage of it. So you can understand that if you want to show that there's bias, sample from population A and population B to show that there could be a difference due to bias. So those are some of the planning considerations. We're going to drill down a little bit more into each. And again, I know I put these as single bullet points, but sometimes they're really not separable, right? So for example, what is the question to be answered and what methods will be used? Here's an example with, they go hand in hand. If you want to, or I actually have three applications here, right? There's progression of DOE. So design of experiments could be used for three things. If you want to do what's called a screening DOE, if you want to identify what factors might have an effect on a particular outcome, you can use a screening DOE. And that helps you kind of screen through multiple factors and isolate down to only one or two key factors that are really important. Let's say you want to characterize your process. You want to understand that magical equation, y equals f of x. You want to be able to understand that if I set the proverbial knobs, right? If I set my process inputs to certain values, what can I predict the outcome, right? And that's where your characterization DOE comes in. Or maybe you want to optimize, right? You want to find the best possible process. Once again, a DOE is a set of tools and methods that are available to you to use, and you can use it to define robust process parameters. You could use it to get the best possible outcome that's predicted within the range that you want. So that's what I'm saying. They kind of go hand in hand. You really can't separate. Once you define the goal or the objective that you want to make, there's usually some natural tools that will complement that. Similarly, I mentioned before, establishing a relationship between two or more variables. In the two variable case, we call it bivariate, right? We have two variables, and we can explore historical data. We can see if there's a relationship, correlation. I hinted at before, correlation doesn't mean causation. It tells you that maybe there's a potential relationship that's worth exploring later. You could do so through experimentation, but you may have some historical data where you can easily do the calculation without incurring the cost of collecting more data. So you can do a correlation study, or you could do a regression analysis, and usually this goes hand in hand with some of your experimentation, so that you can definitively make more of a cause and effect relationship. You could set up confidence intervals, so it's not just point estimates along the line, but some range. And here's again a consideration. If you are doing this, if you're doing a correlation study, take the consideration of just because you see a potential relationship doesn't necessarily mean it's a cause and effect relationship. There could be other factors. Same thing with regression. You can do a study and determine a prediction interval within the range of your study, but be very careful to extrapolate beyond that, because you don't necessarily have that information. So while it may look like it could continue on a particular path, you don't necessarily know that behavior for sure. And if you really wanted to understand that, run another study that goes beyond. But again, if you're looking for a relationship between two variables, these are two methods of several that are available. Graphically, this is kind of what you can see through both correlation studies and regression studies, that characterization, y is a function of x, more so in your regression, through through actual experimentation and not observational studies, you could see if there's a strong relationship between variables. You'll see this also come out in your screening DOEs. If there's a strong relationship, if you have, I don't think I have it in here, but if you have a high R-squared value, that implies that the variation in Y, a certain percentage of variation Y, that can be described by the variation index. So you can have, in the top two graphs, those would have not only just high correlation, but high R-squared values as well. Similarly, the ones down below, it would have either weak or no correlation at all, implying that there is no apparent relationship, and we may want to explore something else. Control charts or run charts, as I mentioned before, are very helpful if, and just run charts in general, right? Anything where time is along the independent axis, the horizontal axis, you could see trends over time. If you're just looking for a general trend, a run chart is just fine, where you just plot the points. If you want to understand if you're operating, if your process is stable, or if you should be, if you want to be able to discern between what's called common cause variation or special cause variation, or even calculate capability, a control chart would be one of the statistical tools analyses that you can use that are available. And then, as I mentioned before, if you want to make a claim about the performance of your process or of what it is that you're measuring, a process capability index or a capability index could be calculated, as could a statistical tolerance interval as well. They both take into consideration the spread of the data, as well as the where the central tendency is, and the specification limits. It's a comparison of spread within specification limits, with a multiple of some sort to ensure that a certain percentage of the distribution falls within the specification. Other planning considerations is going to be around your data. What data are currently available? What are the sources of variation, and what is the quality of the data? And the reason why that's important, this is a very fundamental equation that, if you're going to pull one thing out of this, right, this is probably one foundational thing that you're going to want to take away. And it's this equation of the observed variance. Whenever you're taking a measure, the variance that's observed is a combination from the variance of the actual process that's producing the thing that you're measuring, as well as the variance inherent in the measurement itself. And ideally, what we want to do is we want to evaluate the total variation that's due to the measurement system and ensure that it's small relative to the process. If most of our variation is coming from the measurement system, then you really don't have enough discernment to detect real shifts in your process or real changes in your process. From there, we have 4 key characteristics, and I'll go through these pretty quickly. These are more for reference, but you consider your sensitivity, your reproducibility, accuracy, and precision. Your sensitivity defines the resolution, your ability to detect the measurement difference at certain levels. And there's some general rule of thumbs that you want when you're selecting your measurement system. Sometimes, unfortunately, you find out that the measurement system was already selected and it maybe wasn't sufficient, and you'll have to work with that one way or another. The reproducibility is measure the reliability of the gauge itself, and we assess that typically through a gauge R&R study. The accuracy is an indication of one of the sources of bias that we can have. It could be a bias in the measurement itself. Typically, we'll look at accuracy during calibration of the gauge. And then precision is the spread of the values that can be obtained when multiple measurements are made. It's synonymous with the repeatability, and it's basically a measure of how repeatable one person could take a measurement with a particular method, and that is it's the second R in gauge R&R. So we have repeatability and reproducibility that gets studied in gauge R&R. Again, very common common graphic that you may see that visualizes, helps visualize the difference between precision and accuracy. And either way, you want to ensure that the data that you have, it's good measurements prior to using it in your analytical methods of decision making. The other thing that you want to consider in planning is what are the data that are available, the number of samples, as well as the bias. Those are going to go hand in hand. One, first and foremost, risk-based sampling plans. It is very common that your sampling plan is taking into consideration the risk that's associated with the thing that you're trying to measure. And the reason why you do that, one, you want to be able to make a claim at a certain level, but two, you want to reduce the potential error or bias that can be introduced by the sampling plan itself. Common graphic here, we'll see with sampling error. You can see that there's an actual decision compared to what the correct decision should have been made. We can see that if you make a decision to accept per the acceptance criteria, you decide to correctly accept it when you should have, you made the correct decision. Similarly, if you decide to reject or fail the acceptance criteria when you should have failed it, once again, you made the correct decision. But you have different error types. If you make a decision to reject when you should have accepted, we call that your type 1 error. That's your alpha risk, or the producer's risk, which is false alarm. Similarly, if you decide to accept something when you should have rejected it, we call that a type 2. It's a beta risk, and it's a consumer's risk, or we call them escapes. Depending upon your industry and the application, it's been my experience in med device, type 2 tends to be the more severe type of error that you want to protect against. But there are cases where type 1 may be a little bit more concerning. Understanding the cost of making that error, the implications of making that error, will help you set up proper sampling plan as well. In general, when you're choosing a sample size, we're looking to minimize that alpha and beta error ideally, and we want to provide statistical power, which is 1 minus that beta. We want to be able to basically say a high level of confidence in the claim that we're making. When you're creating that sampling plan, you want to randomize to prevent some of that bias. You want to include all sources of variation, or at least take it into consideration when you're doing that. As I mentioned before, you may want to do it to include all sources of variation so that you have the entire spread, or you may want to stratify by the different sources of variation so that you can isolate those sources of variation, maybe gain a better understanding of them, or just realize that they are and just characterize each stream individually. And at the end of the day, you want to ensure that you have a representative sample that can support the claim that you're trying to make. This is, I know we're running a little bit on time, so I want to just kind of go through, but at a high level, this is another one. You could probably print this up as a reference, leave it on your desk, but just think PGA. When you're doing your analysis, think the PGA. You want to take a practical look at the data. Do we have the right data per the protocol? Was it collected as the protocol said? Are there any obvious errors, mistypes, omissions, anything that was transposed? Just a quick practical glance at the data, making sure that you have the right data. You could continue that analysis in the graphical method, right? So once you take the data from the data sheet and put it in graphical form, you could quickly see if something is not right. You'll see where the central tendency is. You'll see the spread of the variation. You'll see the shape or the distribution of the data as well. If there's any questions, you want to stop there and kind of dive in and maybe resolve them. But if not, then you can go on to the actual analytics. Because if you see something like an outlier, or if you see a bimodal distribution, I guarantee you the analysis you're about to do is not going to be valid. So it's better to understand that quickly using a graphical approach before you move on to the analytics. Then from there, how can you model the data? What are the hypotheses that can be tested? Were the statistical assumptions met? Normality, stability, things of that nature. What conclusions could be drawn from the analysis? Were the assumptions met? Is the analysis valid? And then at the end, what's the claim that could be made? These are some of the graphical techniques. You have the histogram, where you get central tendency, variability, and distribution. These are other forms of distributions you could look at, other ways of looking at it. The nice thing about the individual plots and the box plots is that you can quickly do side-by-side comparisons of different categories. Whereas with the histogram, you could more readily see the shape. You could determine, does it look like it's normally distributed? Does it look like I have more than one distribution? Does it look skewed one way or another? And then the analytical considerations, as I mentioned before, making sure it's one thing to run the calculation and get the answer, but is it a valid answer, right? So sometimes, if you're trying to ensure consistent process performance, you need to check the stability and the capability. And a lot of these statistical methods, whether it's capability or some of these other methods, they rely on an assumption or normality. And if they're not normal, that's fine. Just because the data doesn't fit a normal distribution, there's other methods. But just know that some of the common ones that we use, if there's an underlying assumption or normality, you need to demonstrate that or at least check it. And then when normality is not met, you could use a different tool. You could fit an alternate distribution. You can transform the data, or you can use a non-parametric. So I know I kind of rifled through some of those last parts because I didn't want to leave a little time for Q&A. But in the end, in considerations for planning and analyzing a statistical study, we introduced just the concept of what is statistics, why we use it in the first place. A very basic 3-step process, and then the planning and analysis, right? As I mentioned, we didn't dive into the math. Statistics, in my opinion, is a very practical mathematics that we can use for solving real-world problems. And I wanted to focus more of the conversation around that, having the right data and data analysis, things like that. When it comes to the actual math part, there are plenty of textbooks out there. You might already even have some of that experience, and you could always refer to your friendly neighborhood statistician for any questions. That's all I had for the content. With that, I'll stop the screen share, and or maybe I'll leave the screen share just in case there's any questions pertaining to the content that we can go back to. And I'll open up for questions.
Anthony, so far in the chat, I've just got a comment that basically says, all this is a good reminder of the approach and tools we could and should be using when analyzing day-to-day problems. A lot of times, I claim I do not have enough time and jump to unsupported conclusions.
Completely agree. And my hopes are that you'll see that some of these, especially if you have the data already readily available, they shouldn't take too long. And sometimes jumping to conclusions without data costs you more time in the long run. So I completely agree with the comment that was shared. I thank the contributor for that.
Any other questions before we let Anthony go? I'll give you my own comment. A lot of this, for most of us, I'm sure it seems like the basics, but it's amazing how many times that the basics trip us up. So.
I completely agree. That's what I'm saying. I know I boiled it down to 3 basics, but if you stick with the basics, you won't go wrong.
Any other questions? Okay. With that, we'll thank Anthony for the presentation. That was very informative and be a nice summary for a lot of QEs. I guarantee it. And again, just thank you for the presentation, and we'll see everybody later.